Revis here. In this video, I will perform density, molar mass, and molecular formula calculations from gas laws equations. We show you here some equations for the gas laws. We have Boyle's, Charles, Gay-Lussac's, Avogadro combined gas law. These 5 gas laws are comparative. In other words, you'll always have a starting condition and a final condition. You'll have one set of conditions versus a second set of conditions. So, Boyle's, Charles, Gay-Lussac's, Avogadro combined will always be comparative. That's one way to know you're using one of these laws. Then we have the ideal gas law. PV equals nRT. We also have an example here of a modification of the ideal gas law, which allows you to calculate mass or molar mass. Then we have density formulas here for relating them to ideal gas laws. And we also have a molar mass when we have density. We also note in this one standard conditions. Temperature is 0C, but we always report temperature in Kelvin, K. Then standard pressure is 1 atmosphere or 760 millimeters of mercury. And an STP is important to note that 1 mole equals 22.4 liters. We have a conversion of 1 atmosphere to 760 millimeters of mercury or 760 torr. Note that when we use the ideal gas law equation, there are universal gas constants and we have to match those to the units. That is an important thing to remember, that matching the R universal gas constant to the rest of the units in the problem is very important. Let's do a density problem. Calculate the density of carbon dioxide in grams per liter at 0.990 atmosphere and 55 degrees C. We take the density formula, which we show you here. We show you mass over volume, which equals pressure times molar mass divided by RT, where R is the universal gas constant. We note that we must automatically convert degrees C to Kelvin. That is a mistake that's often made when working these problems. So don't forget, convert C right away to Kelvin. So we take the density equals pressure, molar mass divided by RT. We put in each of the values. We check our units. Our units work out well. And we calculate and report 1.62 gram per liter to 3 significant figures. Notice that we carried out this calculation because we knew the formula that D equal pressure molar mass divided by RT. And therefore, we took advantage of this equation to carry this calculation out in one step. But it could be that, for whatever reasons, you don't recall or know that formula. Then we will use the standard D equals M over V, mass over volume. And in this particular case, we would assume that this gas is operating as an ideal gas, which is a reasonable assumption. So as an ideal gas, we would set this up to solve for volume first. So we would rearrange the ideal gas equation, and we would have V equals N RT over P. We would then look at our problem, and we would put in all the values from our problem. We would match our universal gas constant, R, to the proper units. We've also converted our temperature to Kelvin. Therefore, we calculate the values in this problem and we obtain 27.2 liters. We would then use our standard density equals mass over volume equation, where we would take the mass, assuming again 1 mole under ideal gas conditions. We would have 44.01 gram divided by 27.2 liters for 1.62 gram per liter. So in this case, we use the density equation, mass over volume, since we were unaware of the equation for doing this with molar mass. And we obtained the exact same answers. Let's work a problem involving molar mass and molecular formula. When you have a problem that involves molar mass and molecular formula, it is best to treat them as two independent problems. And that's how we will approach this one. So what's the problem? A chemist has synthesized a greenish yellow gaseous compound of chlorine and oxygen and finds that its density is 7.71 gram per liter at 36 degrees C and 2.88 atmospheres. Calculate the molar mass of the compound and determine its molecular formula. So we will approach this in steps. First, we mark up our problem and we note that we have density, we have temperature, which we've converted to K, and we have pressure. Therefore, we can use the density formula, which states that density equals pressure times molar mass divided by RT. And since we're interested in molar mass, we rearrange the equation to show that density times the universal gas constant times temperature divided by P will give you the molar mass. So we set up the equation, we put in all the values, we properly match our R, universal gas constant, to the proper values in our problem. We convert the temperature of 36C, we convert it to K, and when we calculate this through, we obtain a molar mass of 67.9 grams per mole. So that would be our molar mass. This would be one way to approach this problem. An alternative would be to use the fundamental definition of molar mass, which is mass per mole or gram per mole. And in this case, our strategy would be to consider that 7.71 gram per liter is the same as saying I have 7.71 grams in 1 liter. And my question is, how many moles would be in that 1 liter that contains 7.71 grams? Okay? So in this case, I would treat it as an ideal gas. I would rearrange the equation, the ideal gas law equation, PV equals nRT, to have N equals PV over RT. I would then put in my values, my 2.88 atmospheres, times the 1 liter, which is my assumption. I would put in the universal gas constant times the temperature. When I carry out the calculation, I obtain 0.114 moles. I would then take the mass and divide it by that number of moles, and I would obtain my molar mass of 67.9 gram per mole. So there are two ways to approach this problem. One way to approach this problem is I know the formula D equals density, that is, equals pressure times molar mass divided by RT. And I take advantage of rearranging that equation to solve for molar mass. Alternatively, I treat this as an ideal gas. I then calculate the number of moles using the ideal gas law equation, and I take mass divided by moles and I obtain my molar mass. Once I have obtained the molar mass, I can now proceed to determining what the molecular formula is. So what do we know? We know that we have a compound composed of chlorine and oxygen only. We know that that compound has a molar mass of 67.9 gram per mole. Therefore, my strategy is to simply use trial and error to find a molar mass that matches 67.9 gram per mole. So, I set up a series of trials. In trial 1, I assume that I only have 1 chlorine and 1 oxygen. When I calculate the gram per mole of chlorine plus the gram per mole of oxygen at 35.45 and 16.00 respectively. I sum that and I get 51.49 gram per mole. That falls short of the 67.9 gram per mole. In trial 2, I add 2 chlorines and I obtain a molar mass of the chlorines of 70.90 plus the 1 oxygen, and that mass is 86.9 gram per mole, which is higher than my 67.9 gram per mole, which I know is true for this compound. In my third trial, I use 1 chlorine and 2 oxygens. When I do the calculations, I obtain 67.45 gram per mole, which is close enough to my molar mass that was obtained using the gas law equations. So therefore, the molecular formula for this compound is ClO2. So there you have it, density, molar mass, and molecular formula calculations from gas law equations.